Hello, this is Evelyn Wright, one of the co-developers of the FACETS model. I'm here to show you how to analyze some of the results from our Clean Power Plan Pathways study using a motion chart. The motion chart is a time-animatable scatter plot of scenario results. Each of the colored bubbles you see here represents one scenario, and I can set the variables from those scenarios that we'll look at on the X and Y axes. So right now I have the X-axis set to generation from covered steam power plants, and the Y-axis is set to total power sector emissions, or ELC CO2. With this slider, I set the point in time that we're looking at, and we can move the scenarios forward and backward in time, and we can also play the scenarios forward in time and watch them evolve. I can put a third variable on the chart by setting the size of the bubbles to scale with a variable. So for example, I can scale the scenarios with generation from new gas combined cycle, and we can see which scenarios are adding more new gas than others. Hovering over a scenario shows you its name. This one is named TY for trade yes, shale high, meaning high shale gas resources or low gas prices, EE no, meaning no additional energy efficiency programs beyond those included in the AEO 2015 results that drive our load, and pathway MEX. The Clean Power Plan pathway is mass existing only, and this one has no leakage mitigation mechanism. You can find a full description of the scenarios we modeled and a guide to their names in the paper on our website. You can ignore everything coming after the dashes in the names. That relates to the SENG, or scenario group, a function I'll show you in just a moment. The other thing you can see when you hover over a scenario is the data values for each of the selected variables. So we have 1,225 terawatt hours of covered steam generation in this scenario, 1,824 million metric tons of total CO2 emissions from the power sector, and 813 terawatt hours of generation from new gas combined cycle. Now, the scenario grouping function is highly useful for controlling what you see on the screen. We have a grouping for each of the policy and uncertainty dimensions we assessed in this study, along with one combination. You'll see them listed over here. So the scenario group from 111D trade is whether states are complying individually or engaging in interstate compliance trade. So trade no is individual state compliance, trade yes is interstate compliance trade, and trade X is for the no CPP scenarios, the business as usual scenarios. We have 3 gas resource scenarios based on AEO. So the reference shale scenario is our reference gas price scenario that's based on AEO 2015. The high shale scenario, or high resource case, has low gas prices, and the low resource case has high gas prices. So just remember that what you see here for high and low are referring to resources and not the gas prices themselves. We have 2 options for energy efficiency, and these are applied exogenously. So EE no is no additional energy efficiency beyond what's included in AEO. And energy efficiency yes is that we applied the same exogenous state energy efficiency budgets that EPA did in the regulatory impact assessment. We assessed 6 clean power plan pathways. X is no clean power plan, or business as usual scenarios. We have 2 rate pathways, a state rate pathway, which is RS, and then because S was already taken for state, RB is for the subcategory pathway. So that's the pathway under which units have to comply within their individual subcategory rates. And we have 4 mass pathways here. Mass existing only, MEX, we mentioned already. We modeled this pathway by requiring states to comply with the budgets for mass caps covering existing sources only published by EPA. Now, to be clear, this by itself is not a legal pathway. EPA recognizes the potential for leakage of emissions to new sources when a mass cap covers existing sources only, and so they've required states to use a leakage mitigation mechanism of some kind. So we ran this MEX pathway just to see how much leakage could be expected without any kind of mitigation mechanism in place, and also as a comparison point for runs evaluating mitigation mechanisms. In our paper, we discuss a suite of runs testing a parametric range of incentives to existing gas and new renewable generation, similar to the incentives that might be set up by the output-based allocation mechanism that EPA proposed in the model rule. A separate motion chart on our website shows the results from the full suite of these runs. From this suite, we've selected 2 levels of incentives to include in the main suite of runs. The ME1 pathway has a level of incentive similar to that in EPA's proposal, and the ME2 pathway has a level of incentive much higher. Finally, the MN pathway here is the mass budget with new source complement. So that's the mass cap covering existing and new sources. Finally, we have one more scenario grouping that combines the gas, energy efficiency, and trade dimensions so that we can look at those dimensions in combination with each other. The scenario groupings can also be used to color the scenarios so we can see how the results are sensitive to them. Right now, I have the scenarios colored by pathway. If I change it to shale, we can see we have more steam generation in the low shale, that is the high gas price scenarios, and less steam generation in the high shale or low gas price scenarios. I'm going to reduce the amount of information on the screen by taking the high gas price or low shale scenarios off, and then change the coloring back to pathway. And now let's look at playing the results forward in time. Now you'll see that when we changed coloring, some of our labels for the pathway over here disappeared. That happens sometimes when the graphing widget resizes itself. To correct for that, we can just switch to another view and then switch back to the bubble chart, and you'll see that our legend is restored. Now I've dragged the slider all the way back in time. It's gone to the beginning of 2017. And it's only gone back that far because I have the bubble sizes set to new gas generation, and that's when new gas generation starts. So let me change back to same size for now. And now we can drag the slider all the way back to 2012, which is the base year. So in 2012, the scenarios are all in the same place. We can play them forward in time, and we'll see them start to separate. And then we'll see them start to stratify by gas price scenario. So these are our reference gas resource and price scenario, and these are our high resource or low gas price scenario. The orange ones are the no clean power plant scenarios, and so we'll see those stay in the upper right-hand corner with more steam generation and more CO2 emissions. And we'll see the clean power plant scenarios start to move down and to the left, decreasing steam generation and emissions until the mid-2030s when some of them start to move back upward. So when we get out to 2040, we've got just one group of clean power plant scenarios, the mass with new source complement scenarios, staying at a relatively fixed emissions level because they have an emissions cap on all units. And so this is just a reminder that the Clean Power Plan is not a set it and forget it kind of policy. It will be updated periodically by EPA over time. So let's move the slider back to about 2030 and take a look at the results as of the final compliance period. So we've got our no clean power plant scenarios up in the upper right-hand corner. These are the reference gas prices, and I'm going to set the size back to generation from new gas combined cycle plants. And that allows us to easily see which are the EE-NO and EES scenarios. The EE-NO scenarios have more new gas, and so they're larger than their EES counterparts. So we can see that 2030 emissions under business as usual reference shale conditions and no additional energy efficiency were just shy of 2,000 million metric tons. With higher gas prices, emissions are lower, and with low gas prices and energy efficiency reaching around 1% of load reduction per year, emissions are lower still. Now, among the clean power plant scenarios, we can see that the rate scenarios are very sensitive to gas prices. So these are the state rate pathway, and these are the subcategory rate pathway. And we've got the reference shale ones up here, and the high shale or low gas price down here. So you can see when gas prices are low, we've got at the very low end of emissions and steam generation. When gas prices are higher, we have 300 to 400 terawatt hours more steam generation and emissions of 100 to 150 million metric tons higher. We can also see that between the two rate pathways, the subcategory rate pathway has higher steam generation and emissions when gas prices are higher than the state rate pathway, whereas they're quite a bit more similar when gas prices are low. Now, our highest emissions pathway are this mass existing only with no leakage correction, and especially when gas prices are low and we have energy efficiency no. So this is the trade no and trade yes version of that pathway. Here are the energy efficiency versions, so you can see that energy efficiency is cutting emissions, in this case by about 100 million metric tons, and even more in the trade no version. Here are the reference shale over here, so still the highest emissions scenario under reference shale conditions. And EE is still cutting emissions by about 60 million metric tons a year. Now, as we said before, this pathway by itself is not a legal compliance plan. It needs to be coupled with some kind of leakage mitigation mechanisms. The dark blue scenarios of the ME1 pathway have a level of incentive to existing gas and new renewable generators that is similar to that proposed by EPA in the model rule. You can see that that cuts emissions somewhat, but doesn't bring it down to the level of the other pathways, especially when energy efficiency is not achieved. The much higher level incentive we tested in the ME2 pathway does bring emissions down roughly to the level of the other pathways. And we'd refer you to the paper for more details on how those scenarios were constructed and why the results turn out the way they do. But let's look at some more results from these scenarios. So let's switch the x-axis to look at generation from gas combined cycle units covered under 111D. And I will switch the coloring back to shale so that we can see that the scenarios are quite bifurcated between the low gas price and high gas price cases. So we have quite a bit more existing gas generation when gas prices are low. But we have quite a spread across the pathways. And notably, not all of the pathways induce much of a gas shift. That is, they don't all result in much of an increase in existing gas generation beyond that in the no CPP scenarios. So if we compare these no CPP scenarios with the CPP ones, we can see that the mass with new source complement has roughly similar levels to the no CPP scenarios. The mass existing only with no leakage mechanism actually reduces existing gas generation. The state rate pathway provides a boost of about 100 to 150 terawatt hours per year. The subcategory rate pathway induces quite a bit less gas shift than that. And the ME1 and ME2 incentives are successful to different degrees under different gas prices. So now let's switch to look at new gas generation. And again, I'm going to change the coloring so we can look at how the scenarios break down by gas resource. So we can see, not surprisingly, that in general there's more new gas generation when gas prices are lower, but the scenarios have quite a bit of mixture between them. If we switch to the coloring to look at state energy efficiency, we can see also that the EE-NO scenarios have quite a bit more new gas than the EES. Let's switch this back to pathway, and I'm going to take the high shale scenarios off so we can just look at one gas price scenario and get a sense of the pattern here. So again, if we compare to the reference case levels, the first thing that we can see is that there are almost 200 terawatt hours more new gas generation in the EE-NO business as usual case than the EES. The subcategory rate and state rate pathways both have less new gas than the reference scenarios. The mass with new source complement have slightly more new gas. They're in a similar range though. And then we see that across the mass existing only, there's quite a direct correlation between new gas generation and emissions. That is, these scenarios are all in a straight line together. And the less incentive we have for existing gas and renewables, the more new gas generation we have. If I switch now to look at the high shale scenarios, we see a somewhat similar pattern, but now the rate scenarios have about the same level of new gas generation as in the no CPP scenarios. And we still see this linear relationship across the mass existing only scenarios, but now we've got a more clear split between the trade yes and trade no. So in the trade yes scenarios, we've got slightly higher emissions and usually slightly less new gas generation, although this is one exception. And that's because in the trade no scenarios, more states are citing new gas within their borders as a way of meeting their caps than they are in the trade yes scenarios. In the trade yes scenarios, new gas can be cited in the states where gas is most cost effective, and the allowances that are generated by switching generation to new uncovered sources allows increased covered generation, usually coal generation, to be located in other states. And finally, let's look at generation from new renewables. And we'll see that the pathways stimulate new renewable generation to differing degrees. So if I put the reference and shale scenarios on the same graph again, and let's switch the coloring to look at shale, we've got a very clear bifurcation of the scenarios in that there is much less new renewable generation when gas prices are low, as when gas prices are higher. And similarly for energy efficiency, we see that there is more new renewable generation in the no scenarios. So let me switch back to pathway. And again, I'm going to switch to just looking at the reference shale. So we can see that the rate scenarios and the mass with new source complement stimulate roughly similar amounts of new renewable generation under reference shale conditions. The mass existing only scenarios stimulate quite a bit less, only about a 10 to 15% increase over the no CPP scenarios. And then as we increase incentives to new renewables, we get an increased amount until reaching our level 2 incentives brings us into the same range as the other pathways. Finally, I'm going to change the y-axis to generation from new gas so that we can see the relationship between new gas generation and new renewable generation. And so we can see that there's a fairly linear relationship, and that scenarios that have more renewable generation have less new gas, and scenarios that have more new gas have less renewable generation. And if I add back in all of the different shale levels, we can see that that pattern roughly persists across the various gas resource cases. Now if I color by gas resource, then we see that when gas prices are highest, we have the greatest amount of new renewables and the least amount of new gas, and vice versa. So that's a quick tour of some of the things you can do with the motion charts and some of the results from our study. We'd encourage you to explore the results for yourself. The link to this motion chart, as well as a motion chart exploring the suite of parametric incentive runs, are available on the website, along with the full paper describing our study. You can also find out more about FACETS at our website, or you can contact me at evelyn.l.wright@gmail.com with questions or to set up a time to talk about our results and about FACETS capabilities. Thanks for watching.